Hello there. In this video we're going to look at another method that's a little bit more rapid in terms of convergence for solving algebraic equations. So again, our goal for this video is to solve algebraic equations of the form f of x is equal to 0. And the method that we will be focusing on is the Newton-Raphson method. Alright, so to just begin, recall that solving equations of this form is equivalent to finding x-intercepts of a graph. So we're going to be using this equivalency in order to sort of justify or, get a feel for actually what this method actually is doing. So let's begin by drawing a picture of some function. So let's assume this is our function of interest. Now our goal is to find this value, and I'll explain why we care about that in a minute. So the Newton-Raphson method is going to begin with an initial guess, right? So this is going to be x is 0, so this is what we call our initial guess. So if you're trying to find, say, the square root of 2, maybe you would guess an initial value of 1, 5, 10, or something. You're just going to pick a number. There's some special cases where this number actually does change the value for which this method converges to, but let's assume this initial guess is well behaved, right? So if we look at the curve at this point and consider the tangent line of the curve at this point, right? So this value, of course, has a y value of f of x is 0, and this line has a slope of f prime of x is 0, assuming that this curve is differentiable at this point. So what do we need with this line? Well, we're interested in this point right here. So this is what we're going to call x1. So it's going to be the x-intercept of the tangent line. And then we're going to repeat the process. So we're going to look at the tangent line at this point here. So it's going to have some slope, probably not that extreme, right? And then we're going to find the x-intercept of that line. And ideally, these points should get closer to the point that we want, right? So that's the goal. All right, so let's see if we can generate the equation of this tangent line, this first one here. So we know the point slope form of an equation, using the information that we've given, is going to be f of x0 plus f prime of x0 times x minus x0. So this is like y minus y0 is equal to n times x minus x0 is pretty much that structure. So our goal is to find x1, which is the x-intercept of this curve. So we're going to set this equal to 0, and we're going to be solving for x, which we're going to define as x1. Right? So let's just rearrange this equation in terms of x1. So we have x1 is going to be equal to x0 minus f of xk, all divided by f prime of xk. And this is a very important structure, right? Now, quick side note, notice that f prime of xk cannot be equal to 0. So what does it mean for the derivative at a point to be equal to 0? So recall, we have some curve in space. F prime is equal to 0 occurs most of the time at maximums and minimums, and sometimes at inflection points such as x cubed or something like that, right? So you need to avoid points like this for your initial guess, or you're going to have some problems with this method. So then we can extend this to some arbitrary value, whatever we want. So we have then xk plus 1 is equal to xk minus fxk all over f prime xk. And this is true for k greater than or equal to 1, where x0 is our initial guess. And this is what we call the Newton-Raphson method. So let's just get an idea of how this method works, and in the next video we'll go through a MATLAB implementation on how to program this up. So example, so let's approximate the square root of 5 using the Newton-Raphson method. Sometimes these problems establish some level of accuracy that we want. I'm just going to leave that open for discussion purposes. So to begin, note that the function f of x is equal to x squared minus 5 has x is equal to the square root of 5 as one of its roots. Right? So why do I care? Why do I mention that? So notice that this function f of x has this shape. This here is the point that we want, right? That's x star, namely the square root of 5 that we're trying to approximate. Now, we need an initial guess. Notice, if we choose a point on the left side, it's possible that the tangent line is going to be approximating the opposite x-intercept, which in some certain cases is going to be a different value, and we don't want that. So we need to be choosing a point to the right of this curve. There's definitely some analysis that needs to be mentioned here, but we're going to leave that until another time. So I'm going to choose a number that is greater than the exact value of square root of 5. So we know the square root of 5 is less than the square root of 9, which is 3. So I'm going to be defining 3 to be my initial condition. Also note, f prime of x is going to be equal to 2x. We need this since that's going to be in the denominator of our Newton-Raphson method. And also note that f prime of x is equal to 0 only if x is equal to 0. So as long as our initial condition and any of the iterations do not hit this point, then the Newton-Raphson method should converge, ideally, to something. So let's see what happens. Alright, so we know Newton-Raphson is xk plus 1 equals xk minus fxk over f prime xk. Let's see if we can get a nice compact method for our particular example. So this is going to be xk minus xk squared minus 5 all over 2xk. And then I'm going to decompose this fraction. So we're going to have xk minus 1 half xk minus 5 over 2xk. And then I can distribute that negative to get a nice compact form. So xk plus 1 is going to be equal to 1 half xk plus 5 over 2xk, which is the same as 1 half times xk plus 5 over xk. I guess this is a nice form to work with. And now we can start our iteration process. So we're going to choose x0 to be equal to 3, and then we're going to iterate this many times until we get a value that hopefully is close to what we want. Alright, so let's start the process. So x1 is going to be equal to 1 half x0 plus 5 over x0, which in this case is going to be 1 half times 3 plus 5 thirds. You can do some mixed number operations here, so it's just going to be 1 half times 14 thirds, which is the same as 7 thirds, which as we should know is approximately equal to 2.3. Right, so after one iteration, we have 2.3. Let's continue. So x2 is going to be equal to 1 half times 7 thirds plus 5 over 7 thirds. Again, using some mixed numbers, you can find that this is going to be equal to 47/21, which is approximately equal to 2.238. Right. So after 2 iterations, the only thing that is pretty much the same is 2. We haven't really got any convergence in the other decimal places. So let's continue. So x3 is going to be equal to 1 half times 47/21 plus 5 over 47/21, which again we can find to be equal to 2207 all over 987. So this is approximately equal to 2.236069. Right? Now notice that we at least have 2 decimal places in terms of accuracy, not including the integer place. So the difference in consecutive terms of this iteration process is getting closer and closer to 0. So that's pretty much the idea of how to establish convergence of this method, right? So if you're okay with 2 decimal places, we can say that, square root of 5 is approximately equal to 2.23. Now, outside of this method, you can continue as many times as you want until you get more decimal place accuracies, but actually, this approximation is actually pretty decent because square root of 5 actually is equal to approximately 2.23606798. So actually, even though we do not know for sure, at least from these methods, that these decimal places are correct, they actually are, right? And if we continue this iteration method to say x4 and x5, we should be able to establish that, right? So Newton-Raphson actually converges pretty quickly, actually a little bit more faster than the bisection method, which is great. So again, this Newton-Raphson method is very useful for solving algebraic equations, but it does require an initial guess and some understanding of the behavior of the function in order to establish that that initial guess will converge to the number you want. In the next video, we're going to go through the MATLAB implementation on how to implement the Newton-Raphson method. Hope you enjoy.